think we're live now. Almost on 2 minutes to start. Can folks hear me fine? The chat, okay, if you hear me. Okay, as in, yes, okay, great, thank you. All right, so we'll wait. Well, it's noon already, but we'll give it a couple of minutes, see if more people um, hop on the stream. All right, I think one more minute, and we'll officially get started. Soon people will just trickle in like they do in real life lectures. All right, well, welcome back. This is EECS 281 live from my basement in Ypsilanti. Again, because of that, you might get interrupted by either boys or cats, and so apologize in advance if that happens. So today's lecture is on heaps, priority queues, and Heapsort. It kind of sounds like a lot of topics, but each topic kind of segues nicely into each other. I actually like this lecture quite a bit. Number one, because we do combine kind of the methodology for heaps with actual code in the lecture, as you're going to see. And there's actually some interesting, also theoretical results in terms of runtime for this specific data structure that's a heap that we'll go over. So it's a good mix of kind of theory and practice. It's also probably your first non-trivial data structure that you're going to see in detail, right? I guess it kind of depends on any sort of research that you've done on your own. But if at least context-wise for what's the CSE program, undergrad program, this is probably the first time that you're going to implement a data structure from scratch, like a non-trivial data structure, that provides really insightful theoretical results, as you're going to see. Okay. Also, off the bat, right? Heaps and priority queues are very related in that a heap is effectively a way to implement a priority queue. Again, we'll go over this in the lecture. And then a heap sort is a sorting algorithm that's based on using a heap, right? So everything's related. In fact, the lecture is not that long, but we'll have exercises in between. And of course, this lecture is also very, very important for project 2, which should come out today if it has not yet, where you're basically going to implement, for the most part, everything that we'll discuss today in this lecture, as I recall. And not only that, you will be implementing different priority queues, one of those being a binary heap, which is what we'll discuss today. So this lecture is very relevant to the project as well. But not only will you be implementing the stuff in today's lecture, take a look at the spec whenever it's available. You will be implementing, like I said, different types of priority queues or different implementations of priority queues. One of those being a pairing heap, which we actually don't discuss in lecture. Okay, so you want to jump ahead and start reading the papers on pairing heaps. We will discuss pairing heaps in labs, as I understand, but not in lecture. It is a nifty data structure, more performant than the data structure that we'll discuss today, which is a binary heap. But it is tricky to implement. Okay, so you want to get a head start on reading basically the resources that we're listing out there. You want to make sure you understand the priority queue as it's available in the STL, right? So you can probably want to implement a small program using a priority queue. Again, we'll talk more about that today. So I think that oh yeah, yes, interesting. This heap that we'll be talking about is different from memory heap. Okay, so if you remember from 280, you might have. I'm just reading from the chat. There was either a question or a comment around that. There is a memory heap completely different than the data structure that is a heap that we're going to discuss today. Okay. So on a pairing heap, when you read through that, you want to pay attention to the meld function. It's actually the most important function. It's not the most complicated function. It is, recursive. So, well, I guess there's multiple ways to implement it. One of them is recursive. So you want to pay attention and test that function thoroughly, like unit test it by itself, because it is, the most other functions in a pairing heap are going to be dependent on it, right? So add node, pop, update element, and a lot of these things are not going to make too much sense. I'll make sure to revisit them later when the spec is out. So I'll put these slides back up again in a later lecture once you've had a chance to read through the Project 2 spec. But anyway, just in 281, we definitely want to start projects early, so that's what we're trying to get at. Okay. All right, so let's get started with the real material. And this will consist of a review of trees, which you might recall from 280. I think you also might discuss, I know you go in 203, you do go over graphs. I don't know if you ever get to trees. I don't recall exactly. I know you do look at trees in 280. So it's a graph consists of nodes, and then there's edges that establish some relationship between the nodes. Graphs are a very abstract thing, right? So that's why they're used to describe multiple types of problems, because you can have your node represent whatever, and then you have an edge that represents some relationship between those whatevers, right? Now, a tree is a special kind of graph. It is a connected graph without cycles, right? So if you remember, a cycle would mean you start at one node, then you follow edges, and then you end at that node. That would be a cycle inside the graph, right? You can also look at it as a graph where any two edges are connected by a unique shortest path. In fact, those two definitions are quite equivalent, and you can theoretically prove things for trees using either of those definitions. In a directed tree, we can identify child and parent relationships between nodes. So effectively what that means is that you're in the nodes in the tree, you're keeping track of parents, right? And then, of course, if you have a tree node, you definitely have like some children that you're pointing to from that node. And that's basically what we mean that it's going to be a directed tree, which is, for the most part in this lecture, we're only going to be looking at these directed trees. And furthermore, we're going to be looking at binary directed trees, which means that a node has at most two children, right? So, can either have no children, one child, or two children, but not more than that. Okay, so those trees pretty much a review. We should also review some terminology about trees, just to be on the same playing field, because it's definitely different books that might refer to the same thing with different terminology. So root is the topmost node of the tree. So in this picture, this is the root. A parent is an immediate predecessor of a node. So 2 is the parent of 6, right, in this tree, and it's also the parent of 3, so on and so forth. A child is a node where current node is parent, so that's pretty easy to understand. An ancestor is a parent of a parent, okay? And this is where the description of the tree is starting to hint at kind of a recursive definition of things in a tree, right? So when you start saying things like, well, an ancestor is a parent of a parent, okay? That gets you closer to the root. I mean, as long as you say parent of a parent, you're referring to something that's recursive, right? Descendants is a child of a child, so the other way, but in the opposite direction, which is that you're further from the tree, you're closer to the leaves. Then you have internal nodes, which are, in this particular example, it would be all of these nodes. If I can steady my hand when using these pens. Those are internal nodes. Internal. Oh my God, I'm so sorry for my handwriting on this. The angle at which I write is terrible, so it's hard. And then you have leaf nodes, right? Oh, I might have included some nodes that I did not mean to include. Sorry. So these are internal, right? And then these are your leaves. Again, apologize for that. But all right, so all of that is effectively review. That's, a leaf is a node without any children. All right, so, oops, might have jumped ahead. Now, what you might be familiar with in terms of representing a tree in code, which the customary way to represent it is by using a node struct, right? A tree node struct. So largely you have a pointer to the left child, and then you have a pointer to the right child, and then you have some value that's contained in the node. So here is represented by some class that's called item. and it's given as part of the template. Okay. So a node contains some information, and then you have those pointers to the left and right child. And this is, those pointers is what allow you to efficiently traverse the tree, right? So you can move down a tree from a parent to a child. Again, if we choose, depending on what we want our tree to do, or maybe what algorithms we want to run on our tree, it might be beneficial to also have a pointer to the parent node, so we can easily traverse up. But here, actually, even though I'm showing you this, well-known struct for a tree node, we're actually not going to rely on it. We're actually, in fact, going to stay away from trying to represent trees in this way, right? But this is only in the context of heaps, which I'll talk about in a little bit. Okay, but yeah, just to show you something that you're familiar with in terms of how we represent trees in code. All right, so let me see if there are any questions. Might be some lag and everything. Is the heap a heap? If so, why? The heap doesn't really need to be carefully ordered, does it? Yes, it does. We'll talk about that in a second. Since he stated he was going to release, this is about the release of the, it said the descendant also a child of a child of a child. Yes, yep. Is the root node not an internal node? No, it is not considered an internal node, but depending, and this goes back to the recursive definition of a tree, right? If you take a subtree, right, the root node of that subtree can be an internal node of kind of the super tree that you got it from, okay? That you got that subtree from. Same question. But what about in example? In the example, no, root node is what I pointed out. Okay, that's the root. It's the topmost node in the tree. All right, so I guess this hints at even the questions that were being asked in the chat. Trees are recursive structures. Any subtree is as much a tree as the original, which is why root nodes for a subtree can also be internal nodes. I mean, because the more general definition of an internal node is that it has children, right? The node has children. But conversely, you can have a root node that doesn't have any children, and in that case, it's not considered an internal node because there's no children. It's actually just a leaf, right? Take a tree that only has the root node. And as such, since this is very much a recursive definition for trees, if you will, right? Then all of the properties that we can describe for a tree are also recursive, right? So if you have things like the size, right? So you have a base case for determining the size of the tree, which is just, base case is 0. And then you have the recursive definition for kind of a size function where you would compute the size of a node to be equal to the size of the left child plus the size of the right child plus 1. Okay. And similarly, if you're looking to compute the height of the tree, it's also recursively defined, right? You have your base case, height of an empty tree is just 0. And then height of any node would be the max of the height of the left child and the height of the right child plus 1. And then the depth is, again, recursive base case, and then the depth node would be the depth of the parent plus 1. Okay, so pretty straightforward in terms of the properties. There's actually a lot more properties for trees, but we're not going to be interested in those. More theoretical properties of trees. Oops. Now there are a special kind of tree, of binary tree, that are particularly important for heaps. In fact, heaps are complete binary trees. Okay, so what do we mean by a complete binary tree? Is a tree in which every node has, that's a binary tree is a tree which every node has 2 or fewer children. We've covered that. Now a complete binary tree is a binary tree in which every level except possibly the last is completely filled and all nodes are as far left as possible. So that's a long-winded definition to say that if you were to start from an empty binary tree and start adding nodes to it, the particular order in which you're going to add the nodes to the binary tree is top to bottom, left to right. Okay. So for example, let's say that started from an empty tree and then I added all of these nodes. I would add A first, right? Or have some arrangement in which A is added first, followed by B, followed by C, right? D, E, I, F, right? So in fact, this is a level order traversal of the tree. Okay? And that's basically the definition for a complete binary tree. But so this one in the middle is not a complete binary tree, largely because this node is missing a child right here, right? So the idea is you're not going to add any new nodes to the tree until that level is full, right? So the fact that you have these 2 nodes here before completing this level means that it's not a complete binary tree. And same deal with this example, right? Basically, when we were going to add G to this tree, we should have added it here, right? To make sure that we maintain the complete binary tree property. Okay. So any questions on the complete binary tree? Anyway, so I think I see a few questions about height and depth. Let's circle back on those, right? So given the definition, well, the size is basically how many nodes are in the tree, right? Height is effectively how effectively in what level is the node at, right? So that's level 1. That would be height 1, right? 2. And depth is it's very similar to height, except it's from the parent down. Okay, so that's largely all right. And then let me make sure. Any questions on complete binary trees? What if you move G to the left of C? Would that make it the... Yes, correct. That's what I did earlier. This lag is killing me. Cool. All right, so even though we kind of discussed this node tree representation where we have pointers to left and right, we're actually not going to be using that to represent a complete binary tree. The nice thing about a complete binary tree is that you can represent it instead with an array. Okay, so here is an example. You have this tree on the left-hand side of the slide, and a potential array representation for this tree is given on the right-hand side, right here. Okay, so you can see that the node A would map to the first element in the array. Now notice that this indexing is starting at 1. That's particularly important. Okay. You could come up with a similar representation where the indexing starts at 0, but we're not going to do that because it's simpler, and all we're being wasteful about is just one element in the vector. So we're basically not going to use, right? So presumably there is an element here that is 0. We're just not going to use it, okay? Now in project 2, you can choose to use it or not. It would be up to you, but I like the math where the indexing starts at 1, okay? And what I mean by that is going to be apparent in a second. Is the math to basically go from one node to its parent, or one node and its children, so on and so forth. And notice that, if you were given an array, it's very easy to come up with the tree, right? So if you're given the array A, B, C, D, E, that's given there, then all you need to do is kind of order each one of these elements in the tree, as I mentioned earlier, top to bottom, left to right, which is level order traversal. So you would, that's why you see the ordering is A, B, C, D, E, I, F, H, G. Okay. Similar to the ordering that you have in the array, left to right on the array. All right, so notice that there's no gaps, right? That's because of the fact that it's a complete binary tree, and we need that. We need that. And so the interesting part is that because we have an array, you can index directly into, say, given a node, you can index directly into its parent or directly into its children, right? Which is what I was talking about earlier when I said, the math works out nicer when your indexing starts at 1. Because let's say that you're at node I. Okay, let's say given the index of a node in the tree, let's call this, so a node I. Then you can find formulas for the index to the parent for node I, and that would just be I divided by 2. Okay, and that's integer division is completely fine with that. For that, then if you want to find the index for I's left child, then it's just a matter of doing I times 2. It's supposed to be multiplication. Then if you wanted to find I's right child, then that would be I times 2 plus 1. It's supposed to be a 1. Okay. And so let's do a quick example, right? If I'm looking at D, which is, I equals 4, right? That's the specific index for that node. Then that means that left of at I is just going to be equal to I times 2, which is just 8. Let's see if that's true, right? So 8 is H, and that is indeed true. That is its left child right here, right? And similarly, if you were doing it for right of I times 2 plus 1, which is just 9, right? Which is right here, and it's G, and indeed, if we look at the actual tree drawing, that is indeed its right child, right? So that's really nice, okay? In fact, you can also gather even more information given this indexing, and that is that anything that is a leaf is anything that is greater than the size divided by 2, right? So the size of this is what? 8. 1, 2, 3, 4, 5, 6, 7, 8. No, it's 9. So effectively, anything which are all these leaves, H, G, I, F, right, and E, like all of these are the leaves. That's what I can tell from the picture. And indeed, if I did 9 divided by 2, then integer math gives me the right index to know where the leaves are at. So anything that would be greater than 4 is a leaf in terms of indices. Okay. Cool. Any questions about the math for binary heaps? Yeah, I clarified the day in which I think we had it today in the schedule. If Dr. P mentioned anything else, I would go with what Dr. P mentioned. I was just going by our schedule, and it might have shifted a bit. So I don't know if somebody in the, let's see. Yeah, I'll. Can somebody from the staff that's in the chat ping on Slack and see if we can get a definite date so we can announce it here? All right, so there we go. So quite a bit of information that we can gather by just doing, integer arithmetic. So that's a big benefit of representing a complete binary tree using an array. In fact, there's almost no reason to use anything other than an array to represent a complete binary tree. Everything else is much more inefficient, right? Here, there's no pointers, so there's no extra memory. There's no traversing of pointers that you need because you can just random access directly into the parents and the children, okay? All right, so a complete binary tree is actually what we're going to use to represent a heap, but we also need to introduce what we call the heap ordering constraint. Excuse me. If a tree is heap ordered, and here in parentheses you see that we have max, and that is because you can actually have max heaps and you can have min heaps. Okay. Everything works out the same except that we would change, how we compare things, whether it be a max heap or a min heap. For the rest of the lecture, we're going to assume that we're going to be dealing without loss of generality with max heaps, right? Again, it's a matter of what comparator you use. So you can assume that if you were implementing this, there would be a functor. That's what you would use to actually compare the elements as you do all the logic that we're going to talk about in this lecture. Okay. All right, so what is this heap property? That is each node is not greater than the priority of the node's parent. Okay. So here we're going to use the value of the nodes as the priorities themselves, but that's not necessary. You can have, right? So instead of our example just being a simple integer, it's a simple array of characters in this case. Each one of the elements can be structs, and then the struct has a priority field and then the actual value field, right? But to keep it simple in this lecture, then we're going to assume that the priority and value of the node is the same thing, right? So we keep it simple and then we just use integers all throughout, okay? But in general, it doesn't have to be that way. You can introduce structs in there. Cool, so let's see what we have here in this example. We have a tree on the left-hand side, complete binary tree. So in fact, we can use that to potentially use it for a heap. And then on the right-hand side, we're basically assigning some priorities to each one of the nodes. And so the heap size here is 9. I mean, it's similar to the example that we had in the previous slide. And now let's say that our priorities are, 81 is the root node. That's a priority of the root node. And then 18 is the priority of its left child. 14, the priority of its right child, so on and so forth. Okay. And the heap property is basically that if I pick any nodes on this tree, none of its children or grandchildren, for that matter, so descendants throughout, are going to be higher than that. Their priority is not going to be higher than that current node. Okay? So if you pick 18, you'll see that all its descendants, so 9, 7, 2, and 4, they're lower than 18, right? And that's effectively the heap property. You know, and you can prove this by induction. You know, if you're so 203 inclined, that, you know, this is what all of these nodes obey, right? The way that we have it in this example. And that's a heap property, so it's pretty simple, okay? Now, make note, this is very different than your binary search tree ordering property, okay? Remember, in a binary search tree, which is completely different than a heap, okay? So don't get them confused. In a binary search tree, the constraint, okay, or the ordering property, is that for any node, anything that's on the left subtree is less than the current node, and anything on the right subtree is greater than the current node. Okay? So that's different than this constraint, where we're saying that both children and their subtrees are going to be less than the current node. Again, assuming it's a max heap rather than a min. If it was a min heap, it's the other way around. All right, so to summarize, heaps have two crucial properties that we need in order to make heaps work. You have completeness and you have heap ordering. Okay, so completeness is what we just talked about, the complete binary tree, and then the heap ordering is that constraint that I'm introducing into the tree, where any children of a current node is going to be less than the current node. Okay. And then what we're going to do is leverage these two properties to create an efficient priority queue, right? Because as I mentioned earlier, that's what heaps are. It's effectively an implementation for a priority queue. So first we're going to look at a couple of operations that we need for heaps. And then we're going to look at some additional operations that are going to be introduced as we use heaps for building a priority queue. Now, as you can imagine, tons of situations where you can break the heap ordering constraint, right? After all, it's an array, right? So if I go into the array and I change one of the priorities, I can effectively break my heap constraint. So what we're going to do is introduce operations that, given a breakage of the heap, we should be able to use these operations to restore our heap order. Okay. So here is the example that we had earlier. Heap size is 9. Then we have, this is effectively the same example. And then the array representation on the right. Okay. And again, notice, very important, that this is starting with index 1 rather than index 0, right? Otherwise, the code that you're about to see is not going to work out, right? So you have to assume that indexing starts at 1 rather than 0. Okay, so what we're going to do is introduce operations to fix the heap ordering properties in order to then add operations for a priority queue. So what we're doing conceptually is we're starting with arrays or trees, which are kind of like how you can implement a heap, right? So we're going to use either arrays or trees, but really no trees. You could use a tree. You don't really want to. So we're going to stick with arrays and using array. Oops. And then using arrays, we're going to introduce the operations for maintaining our heap constraint, so that now our simple array is just going to be a heap And then from a heap, we're going to have a priority queue. And in fact, after that, we're going to discuss how we can use a heap to do heap sort. Okay. And as I mentioned earlier, you can have max heap, you can have a min heap. Due to my accent, I might say min heap, which, it doesn't mean it doesn't mean that you have a mean heap that's mad all the time. It's my accent. I'm trying to say min heap, and sometimes I'll say mean. So I apologize for that. All right, so let's see. How can we break? So given an array that we are assuming has our heap ordering property, okay? What if we break it? Like, so for example, let's say we go in there, right, in that array, and we take one of the priorities and change it. And the first example that we're going to pick is that we change it by increasing it, right? So let's say that we're taking heap 8, so that's this right here, and we're changing the priority from 2 to 35. Okay? How would we go about fixing that is the question. So here we'll discuss what we could do conceptually, and then in the next slide, we'll look at code for actually doing this. So the first thing to do this as an exercise is to, and here let me change my color. Right, so first thing, I'm going to do 81, right, and 18. I'm just copying the tree on the left, so everything. 2, 4. All right, and now, given this operation right here, what we're doing is changing 2 to 35. And that breaks my heap constraint, right? Because now I have 9 as the parent of 35. We can't have that, right? So how can we fix this? Anybody can suggest what could be done here? Let me see. I see a couple. Do we store size? Yes. Size? Yes. Please do. You'll do it in project 2. You'll store the size, meaning the number of nodes that are currently in your heap. Okay, and you should avoid using .size on the vector. Switch them. Yes. Very good. Move it up. Yes. In fact, it's more of a swap, right? Because what we would do then is now 35 becomes 9. Oops, not 95. $35, oh my God, it's now 9, and then 9 becomes 35. And then am I done? No, I'm not done because I still see a break, right? So basically, now this becomes 18, I think is what I think I wrote, and then this becomes 35. And now I'm good. Right? And now the heap constraint is satisfied throughout. Okay. So, actually that wasn't too hard, right? So conceptually what we're doing is if the heap constraint is broken by an increasing of the priority, then what we have to do is basically look at that node's parent and see whether I need to swap given, whether it's greater than or less than. Okay, if it's less than, I don't need to swap. Sorry, if the current node is less than, I would not need to swap. But if it's not, then I do need to swap. And then do that recursively going up, right? And then I would stop when I see no need to swap. And that is the code that's summarized here. And we call it fix up, right? So You have you basically take the heap as input, and just that might make it readable. So item, recall, is just basically some struct that exists that's meant to hold the elements, right? And then heap is the array for the heap. And then K is basically the current node that we're looking to fix. Now, this could be implemented recursively, but you don't need to, right? Since we have an array, then we can just use a while loop rather than implement it recursively. Conceptually, it's really a recursive operation that would happen, but no need to use recursion on the implementation. So while K is greater than 1, that is basically, while we can continue looking for things to potentially fix, check if indeed I need to make the fix, right? Notice that this is the K divided by 2 is parent, right? So basically I'm comparing the parent against the current node. If the parent is less than, then I need to swap, right? So that's where I would do my swap with the parent. And then this would move up to the parent. And rinse repeat, right? Until either I have nothing to swap because the constraint is satisfied, or K is 1 or less, okay? Which means that you've gone all the way up to the root. So pretty simple, okay? Very efficient code too. Can anybody point what's the runtime of this operation? Give it a minute. This lag is weird. So I see a question. What if you lower the priority of a node and its children have a higher? Yep, we're going to get into that in just a second. But first, we've discussed the situation in which we increase the priority. And so we're using this fix up operation to fix that. Basically, to summarize, is we need a different operation to fix the situation that you described, Aditya. Okay, log in. Yes, yeah, true, log in, and that is because you have this right here. So K divided equals by 2, right? So you're basically making jumps in the array. And so by dividing by 2, you're making large jumps. And so that points to a log. Cool. So yeah, this entire operation is O of log n. All right. So that's the case in which we're increasing the key. And I think this question was asked, what if we decrease the priority? What happens then, right? And off the bat, I'll say, so it's basically the analogous, there is an analogous solution, but it's a little bit trickier because when we were doing fix up, right, when the situation was increasing the priority, it's a little bit easier because we only have to compare to the parent, okay? But when the situation is that the priority is decreased, then we have two choices. We have the left child and the right child to kind of look at to decide which one we're going to swap with. But it is analogous in that what we're doing is swapping with a child. So instead of swapping with a parent, we're swapping with a child. So the logic is a little bit different because of that, or maybe I would say a little bit more complex, but not terrible. So we'll look at the code, but first, conceptually, what would happen, I'm going to 81, 18, 14, 7, 5, 4. Okay, so what we're looking at here is at 2, I'm changing 18 2, 3, right? So what we're looking to do is, boom, do that. Okay, so that immediately breaks our heap constraint because we've lowered from 18 to 3, and then we definitely have children 9 and 7 that are larger than 3. Right? All right, so what do we do then? Like, what would you suggest we do? Given that we have 9 and 7 to pick from, what would you do? Right. So we know we don't have to fix up, right? And that's because the parent is 81. Nothing to do there. And in fact, we don't even have to check that. The fact that we're decreasing the priority tells us that we should be swapping with children rather than swapping with parents. So we don't have to worry about checking against 81 at all. Now what we have to worry is checking against 9 and 7. So we have swapped with max of children, and that is correct, right? So what we would want to do is then take a look at 9 and 7 and just pick the max of the two. That would be 9, right? So now we have 9 here, and then this becomes 3. Oops. Okay. And then we apply this recursively. We would check 3 against 2 and 4, right? We would determine that 4 is greater than, so then this becomes 4, and this here becomes 3. Okay. And now, if I check everything and I didn't mess anything up, I think our heap invariant is maintained, given the change. Yep. Cool. Yeah, so only a little bit more complicated when we're decreasing the priority, and so the function looks like this. A bit more involved, but it's really conceptually the same thing, except going down the tree rather than going up. So the fact that we're going down the tree, we call this fix down. And if we're going down the tree, it means that you have times, instead of doing k divided by 2, we're doing 2 times k, right? So 2 times k less than or equal to size. So this is analogous in the fix up code when we were checking whether k was greater than 1, right? But since we're going in the other direction, now we need to compare against heap size. Okay, so we would actually, well, I'm saying traverse, but this is not really traversing. It's just, let's just fetch the index of the left child. That's what we're doing right here in line 3. And then we have our check whether j is less than heap size. That's just so we know we're not going out of bounds. And then this is effectively the, so instead of, I know in the example I mentioned getting the max of the two. Don't really need the max. I mean, you are effectively taking the max of the children, but you don't need to call on a max function and pass it to 2 children. All you need to do is from the left child, if you check and the right child is indeed greater, right? So that's, this one's left and this is right, right? If you recall from our indexing, let me write it here, right? We had that left is equal to 2 times I, right? Which is what we're doing here. And then right was 2 times I plus 1, right? So that's why we have j plus 1 here, because we had j equal to 2 times k, right? And so we're basically kind of here first assuming that the left child is the larger one, but if we find that it's not, then, you know, we go with the right child by just increasing j, right? And once we've done that, then we need to check whether the right child is indeed greater than the current node. If the current node is greater, then there's nothing else that needs to be done, right? We have no children to swap with, right? So we break, right? But if not, then we would go ahead and do the swap, right? Similar to what we did with fix up. And then we said k equals to j, which is moving to the node that I just swapped with. Okay, and that's moving down the tree. And so that's our code. And again, I won't ask it on the chat for in interest of time, but this is also a log n operation. Right? Okay, because at every point I am doing 2 times k, right? So large jumps, and we do that a logarithmic number of times. Cool. Let's see. Any questions? What is the difference between break and return here? I don't think there's a difference. Yeah, there's no difference. There would not be a difference. You can just do a return. Yeah, so Aditya is correct in that that's the difference. That like if we have this break here, this will break out of the loop, but you can see like right after we close the loop, we're closing the function. So conceptually, for this function specifically, it's the same. Would have the same effect. Yeah, I think somebody else replied on the chat. Cool. All right, so now we have 2 functions for fixing a heap, and that's what we need in order to implement a priority queue, right? So a priority queue in general is a data structure that supports 3 basic operations, namely insertion of a new item, right? So we basically need to add to our priority queue. Inspection, which is basically looking at the top element, and then in it's the top element in that it has the highest priority, right? So that's going to be key, because what we want with a priority queue is fast access to the most extreme element, if you will. Okay, and we say most extreme because remember, you can have a priority queue that's looking for the highest priority, or you can have a priority queue that's looking for the lowest, right? And priority queues are actually quite important and often overlooked in interview questions, right? So I find that when I've interviewed folks, the question would be rather simple to answer if the interviewee would have thought up a priority queue for the solution. And instead, it's very easy to kind of just veer off into kind of creating your own data structure for identifying, the priorities that the context of the problem might be asking for. Whereas oftentimes in interviews, if you can say, well, I'm assuming I'm using a priority queue. Right? So oftentimes overlooked in interviews, and also because later on in the course, we're going to have algorithms that do depend quite a bit on priority queues, namely shortest path in a graph, in a directed graph, and Dijkstra's algorithm, okay, which we're going to cover later on in the course. So quite useful. And priority queues are often implemented using heaps because it's very efficient. They're very efficient, very easy to implement, as you'll see in, well, a binary heap, very easy to implement, not necessarily a pairing heap. All right, so in a priority queue, this was from a previous, let me erase some of this. Mistakenly saved a bunch of this. Oh. Dang it. Is it erasing? Oh, it was saved like that, so it's not letting me erase. Oh, well. All right, so what do we do in order to insert into a priority queue, assuming that we're implementing it as a heap, right? So here at the top, we have our array, okay, for our heap, and it's representing this tree on the left. And what we're looking to do is to push the value 100, okay? And the way that we would do this, well, first we're going to assume that we have some extra capacity in our vector, right? Because basically if our array or vector was up to that item indexed by 9, then we would not have, our heap would be full, right? We're assuming that there's additional capacity such that we can push a new value into it. So hence these 2 extra slots here on the right. And what we would do is effectively just say, okay, I'm going to do a pushback, right? Assuming that this is a vector. I can do a pushback and put the value 100, which is what I'm looking to push, right there, okay? And if I do that, that conceptually means that I am adding a left child to node 7, right? So I'm going to draw it on the left picture. So what we're looking to do, and this looks, it's meant to be left, but since I don't have space, I'll do it like this. So that's what we would do. So by doing a pushback, which means just put it at the end of the number of elements that I have, right? So that would be slot 10. Excuse me. Now, if I do that, that can break my heap invariant. And sure enough, conceptually, with the tree that I have on the left, now that I've added the node 100, there is a breakage there of the heap constraint, right? Because you have 100, that's a child of 7, okay? So what do you think we should do? How would we fix this? Anyone on the chat? All right, in the interest of time, I'll just go ahead, because yeah. Well, that's what we had fix up for, right? So that's effectively what we would do is the first thing, push back at the end of the number of items that I have, and then fix up. So that would mean that I have 100, which I would decide to swap with 7. So 7 comes down here, and then we have 100, okay? But then I'm not done, so then I would swap with 18. So now this becomes 100. And then again, now this becomes 81, and this becomes, it bubbles actually all the way up to the top of the tree. It becomes our new most extreme element. Okay, that notice we would have fast access to, because basically our top operation for our priority queue, if we're using a binary heap, is to just look at the element indexed by 1, right, which is the root. Okay, so that's constant time access to the most extreme element. Okay, so this is the code. Oops, there's a bit of lag. What's going on? There we go. So here is, oh, dang it. Here is the code for push of a priority queue, assuming that you're using a binary heap behind the scenes. So this is basically adding the new element to the end of the vector by pushback. I mean, you could use pushback, but here we're doing it with a straight up array. So we're just doing plus plus on the heap size, right? So increment heap size by 1 because we're adding an element, and then index directly into that array slot, and then assign new item, and then do heap size you fix up on the heap size, right? Remember, this is now the index of new item, right? Cool. So fairly simple now that we have the fix up function. So always insert at the leftmost available index, then bubble. Yes, correct. Well, it depends on whether you're talking by leftmost. Depends whether you're talking about the tree or the array. So in the array, it would be the rightmost element where you insert it, right? But it is true that if you're talking about the tree, well, not even if you're talking about the tree, because you could also be, if the left child is taken, then you'd have to go with the right child anyway. But in the tree concept, you would be always inserting into the tree, top to bottom, left to right. So level order. It's easier to think of it in terms of the array. Just insert it at the end of the array. All right, so deletion, which is another operation that we need to support in a priority queue. So again, this is a situation that's analogous to the previous situation that we saw. And as you can imagine, this is code that's going to involve fix down as opposed to fix up, right? And the way that we would do this is effectively the following. What we're looking to delete, right? Remember, in a priority queue, when we pop, we're also always going to be popping the most extreme element, and that is the element that sits here, right? At index 1. So what we're going to do is, since we're popping it, right, we're going to say, all right, I'm going to just take the rightmost element in the array, which is 4. I'm going to swap it here, right? So now 81 becomes 4. And then I fix down. Okay? That's effectively what we do. Here, what we would, I guess it's a little bit confusing on the right because I already written kind of the swaps, right? But what we would do is basically delete the 4 here, right? Which becomes the root of the tree, and then fix down, which it would be swapping with 18 because 18 is larger than 14. So now we have 18 here. This becomes 4, but we still have breakage in our heap constraint. So 9 is greater than 7, so that's what I'm going to use. So now, 4. And then I'm done, right? Remember, because we moved the 4 to the root of the tree, there is node here. Cool. And notice that when we do this in this fashion, the complete binary tree constraint is also maintained, right? That's why we're always picking the rightmost element in the array, which would be the last element from the level order of the tree. Okay. All right, so that's deletion. The code for that would be here. And you see that it's quite analogous to the code for pushing. We call it pop. So this is the swapping, the basically last element in your heap with the root, and then you do fix down. Okay. All right. Any questions? Yes, I'm about to go into Heapify. Actually, there's a nice picture for you before we go into Heapify. All right, but any questions? So now we basically covered all our operations. Actually, I'll go back. We mentioned 3 important operations. We've covered push, we've covered pop, and top is so simple. Again, it's just looking at the element indexed by 1. Okay. So we've covered all 3 operations, so we can definitely implement a priority queue. Okay. And you'll be doing that for project 2. Now, the question arises, if I had a random array, okay, that I want to turn it into a heap, what is the best approach to doing that? And that is where Heapify comes into play, because I see a couple of folks already asking about Heapify on the chat. Let's see, I have a question. Do we swap with the rightmost element because nothing depends on it, as it has no children? Yes, I mean, that is a reason why we would pick the rightmost. It's not the only reason. Like, if we pick the rightmost element, we're very sure, right, that if we sit that rightmost element, since it's a leaf, meaning since, it doesn't have any children that depend on it. When we place it at the top, we'll be able to do a fix down correctly to bubble it down to its rightful place, if you will. Okay. I think that is so we maintain the completeness representation invariant. That is true. That is another reason why we would do that. If we pick the rightmost element, then it guarantees that when we do our fix down or bubbling down from the root to wherever its position should be, we don't break the complete binary tree. Okay. All right, so on with heapify, okay, which is a rather important operation with heaps. It is going from a random array of integers and then transform it so that it actually represents a heap, or sorry, that it satisfies the heap constraint and that it represents a part, a heap. Now you can imagine there's multiple ways of doing this, right? You can imagine that you can say, take my random array, basically iterate over each element in the array, and then start with an empty heap, and then each element that I read off from the random array, I just push into my separate heap array, okay? And I insert using the push operation, right, that we went over. Yeah, and so that operation, you can imagine, is n log n, right, assuming that the size of the random array is n. That's an n times log n operation, because for every element in the random array, we're going to be pushing, and we know the push operation is log n time. Well, actually, that's something that we might have not explicitly stated, although it's kind of implied with the code. Pop, since it relies on fix down, and this is constant time, this is a log n operation, okay? You might have picked that up. It's kind of implicit from the code, but just to state it cleanly. And same deal with push, right? We already discussed the fact that fix up is log n, and this is definitely a constant time operation, so this is log n as well, okay? So so that approach is rather wasteful because you're creating a separate array for the heap. So there's better approaches. One approach can also be, I can sort in reverse order, and it's not hard to tell that an array that's sorted in reverse order would satisfy the heap constraint. Okay, I'll let you do that as an exercise. But of course, even though we have an improvement in memory because we're not using an extra array, we can do the sorting on the same array that we're using for the heap. The issue with that is that it's still n log n, okay? But in fact, we can actually do this operation in linear time, okay? So let's go over that a bit. There's actually 4 different ways that you could do this. 2 of them would not work because there's no real way to maintain the heap invariant consistently with 2 of those approaches. Then 2 approaches would produce a valid heap, but one is more efficient than the other. Okay. All right. So the approaches are called bottom to top and top to bottom. Really, what this amounts to is top to bottom is I'm iterating over the heap array from left to right, and bottom to top would be I'm iterating over the heap array right to left. Okay. The reason why it's analogous to top to bottom and bottom up is if you've been following, you can easily tell that in the array that represents a heap, the elements that are closer to the root, so at the top of the tree, are to the left of the array. And again, actually, from half of the array onwards, those are all going to be the leaf, right? So they're going to be at the bottom of the tree. All right, so if you proceed bottom to top, doing repeated fix up, that would produce an invalid heap, and I'll let you try it for this example. It's not hard. Again, bottom to top would mean that I take this array and I iterate left or right to left. Okay. Basically, the idea is I would look at each element and decide whether I need to do fix up. Okay. Then you can try top to bottom, which would mean that I go from left to right. Okay. Trying to do repeated fix down. Okay. So if you do that, again, you had like a for loop, and for each element, right? So it would look something like this for each. I'm going to write pseudocode for each element in, I'll call this A, in A, right? You would try to do something like fix down on E. Okay, that's pseudocode, but you get the idea. So it's really just a for loop. That would also produce an invalid heap, right? So that's not guaranteed to work. There's an example for you to try to convince yourselves that those approaches are not going to work. You can proceed top to bottom doing repeated fix up, okay? But that approach is going to run you in n log n time, okay? The way to see this is because I'm going from the top of the tree down, I'm kind of guaranteed the worst case in the number of fix ups that I would have to do in order to fix my heap invariant throughout the entire tree. Okay, so this is no better than just sorting the array in reverse order, right? Which we talked about earlier. So let's look at actually the most optimal way to do it, which is in linear time. Let's see how that works. It says we have here that it's an ugly proof, but it's not that bad. So we'll go over it real quick. And also, STL does have a function that's called make heap. So you give it a random array of integers, and you call make heap, and the output is going to be an array. Well, the same array, except elements have been shifted such that the heap invariant is maintained throughout the entire array. Okay, and it runs in linear time. Okay. All right, so let's see how this actually works so let's first do an example, and then we'll come back to kind of doing the analysis to see how that adds up to linear time. Okay. So basically what we're looking to do is for each element, again, this is pseudocode. For each element in A, let's call this A, I'm going to iterate right to left. Okay. And then what I'm going to do is fix down on E. Okay. So that's the pseudocode for what I'm trying to do. What that means here with this code specifically is the following. Now this is easier to interpret if I draw the tree rather than work on the array specifically. So assume that's the code, that's a pseudocode that we're going to apply to make our heap. Okay. So I'm going to erase it for a second because I don't have space here. Okay. So now we have our tree, and it's very easy to construct the tree. I just read left to right to construct my tree. That's 1, that's 7, that's 9, that's 14, that's 18, that's 81. Okay. So what this means is then that I would, if you follow the pseudocode that I wrote earlier, I would go right to left, trying to do a fix down. Okay. So I would look at 81. Okay. and try to apply a fix down there, but there's no fix down to apply, because if remember, fix down, we needed to look at children. 81 doesn't have children, so there's no fix down to do. And you might be, well, what's the purpose of that? Well, I mean, this is the advantage of doing this bottom-up fix down approach, is that you actually get to start in your iteration, you actually get to start at half of the array, because there's nothing that you need to do for the right half of the array, because those are all leaves. They have no children. There's no fix down to apply. Okay? So, but conceptually from the pseudocode that I had, you would basically just visit each element and go like, well, I have nothing to do for 81. I have nothing to do for 18, nothing to do for 14, or 9, or 7, right? So nothing to do for any of those, okay? But if you were, instead of writing pseudocode, you would actually write an implementation. Basically, you would immediately jump, right? So you start for loop at parent of heap size. Okay. All right, so now I got into 1. And there is something that we should be able to do there in terms of fix down, right? I would basically fix down with 81, right? So now my tree is 4, 2, 5, 81, 1, and 18, 9, and 14. Okay. So that's what I did with 1, right? So if you were writing this in array form, you would swap these two. That's what I just did. Okay. And then I would continue. So I'm done doing fix down for 1. I would now do fix down for 5. Try to use a different color, right? And fix down for 5 would mean that I would swap with 14. Okay, done with that. Then I would try fix down for 2, right? So that means that 81 comes here, 2 moves down here. And then I would try fix down on 4. So 81 comes up here, right? And 4 comes down here. So notice that as I was iterating right to left, right, I did not have to bubble all the way down, right? Every fix down that I did was with the current node with one of its children, and that's it. I didn't have to bubble all the way down. And that's the big advantage of this approach, right? And that's what's going to give you a linear runtime. So if we do the analysis, what we're going to have is that for any tree, the bottom, which are all the leaves, right? For the leaves, in terms of number of swaps that we would have to do, that's n over 2, because that's how many leaves I have. If you remember, I said that for I greater than heap size divided by 2, those are all leaves. Okay, I have to do 0 swaps. Okay, for at the and this is level n. Oops. And this is level n minus 1. Oh, actually, I won't use n. I'll use k. Oh, this is so much easier on a whiteboard. Here, I had to do how many swaps? I only had to do 1 swap, right? And then we have the next level, which is n over 8, 2 swaps, and so on and so forth. Okay, all the way to the top. Okay, so what we have then, if we were going to add all these operations up, right, we would have the sum over n over I, n over 2 to the I, times I minus 1. And this goes for I equals to 1 to k equals to log k, log n. Okay, so, and if you do some math trickery there, okay, if you do some math trickery there, this actually comes out to be O of n, okay, and we won't, this is not 203, so we won't go over that math trickery, but you're free to look that up in either CLRS or plenty of resources online. But all of that adds up to O of n, okay? Actually, more precisely, it's like n plus log n plus something, which is O of n, okay? Let's see, what about the 18 at the bottom? Oh, is that for the, let's go over that, yes. Oops. What about the 18? Oh, yes, you're correct. Sorry about that. There is a swap that I missed, which was 18 comes here, 2 comes down here. You are correct. Thank you for acknowledging that. So the fixed down, when I got to the fixed down from 2 would have bubbled twice, right? This is a scenario in which we do happen to swap 2 times to the bottommost level, but on average, the number of swaps that you have to do is much less than having to bubble it all the way down, right? It's on average because we're assuming random input for the array. And so that's basically the analysis. It's a kind of hand-wavy analysis. We haven't discussed how we jump from this to O of n, from this equation to O of n, but again, feel free to look that up. Okay. All right, so in the interest of time, I'll just jump. Oh, that's the solution to the exercise that we just did. So it's, you have a plain clean, and sure enough, I might have missed some swaps as I was doing it live. But this is the final solution of doing the previous exercise, which is bottom up, fixed down. Cool. All right, so we'll finish right on time with Heapsort, and you'll be like, oh my God, we're gonna discuss Heapsort in only a couple of minutes. And really that's all we need, because with what you know from heaps, if I told you, come up with an algorithm that uses heap to sort an array, then it's not hard to think about it and say like, well, if I always have access to the most extreme element, right? All I would need to do is basically take my random array, make heap, and then pop every element from the heap, right? And then every element that I pop is going to come out in order. And sure enough, that's effectively Heapsort, okay? But because we know of the heapify operation and we know the internals of the heap, we can come up with more efficient code than that. And so that basically means that our Heapsort algorithm just, well, we take as input the heap array, heapify, and then all that is left to do is basically pop every element from it and place it in order. That's what this accomplishes, right? So basically swapping with the root element is popping each element in turn, but after each pop, because I'm swapping, you have to do a fix down to maintain the heap property. So notice that lines 4 and 5 is effectively the same thing as doing a decrease key, right? If you go back to that function, which was, not decrease key, excuse me, deleting from priority queue. If you look back at that code, lines 4 and 5 are effectively the same code that we had for that function. So yeah, and that's Heapsort. And notice that we have no extra arrays, right? We worked on the same array by doing heapify, and then we have a for loop where we just do one swap and fix downs, right? And none of those required some extra larger size array, right? Everything was kind of done in place on the same array. Okay. So any questions about Heapsort? Doesn't class end at 1:20? I did start a few minutes over on afternoon, but I'm effectively done. Extract max, then heapify. Not sure whether that was related. Michigan time isn't necessarily anymore. Sure it is. There are still person classes happening. Maybe you can be outside your person class starting at 1. I don't know what that's about. But we're effectively done. Any questions about Heapsort? All right. Well, I'll leave you with the summary of what we discussed. It's a good summary to keep around as you go into Project 2. Again, all of this you will implement for Project 2. So you will be quite familiar with this code by the end of Project 2. Okay. Is this our fastest sort now? Yes, at the moment, this is the fastest sort that we know of. As of next lecture, we will be covering a bunch of other sorting algorithms that are basically just as fast as Heapsort, and you would want to use instead of Heapsort. But there are situations in which Heapsort is your best option. Can you quickly explain the swaps again? Okay, so I'm done with lecture, so feel free. I can answer a few more questions before I officially leave. Can you quickly explain the swaps again? Yes, sure. You mean the swaps for the heapify, Aditya? Just want to make sure we'll be talking about the same deal. Lag. Oh, for Heapsort. Okay, not for heapify, for Heapsort. Okay, let me go back to Heapsort. Okay. So maybe this is easier way to interpret it. I'm going to go back to the slide on deleting from a priority queue. Oop, here it is. Right, let me just remove all of this. Oh, that's not what I meant to do. Notice that here, this is the pop operation, which is deletion from a priority queue. Again, assuming that we're using a binary heap. Line 2 is the same thing as a swap. In this context, the thing is we don't really need to swap here, but it acts as a swap in when we're doing heap sort. Okay. Remember that the trick here was we were taking the last element in the heap and we were placing it at the root of the tree and then just doing fix down from the root down. Okay. So that was deletion. And remember conceptually what we said the heap sort algorithm was, well, I create a heap and then pop everything from the heap in turn. Right. So while my heap is not empty, I pop. And because popping always extracts the most extreme element, then you can, by induction, prove that the elements are going to come out in sorted order. Okay? So keep those two lines of code in mind, and we're going to compare them to the code that we have for Heapsort. We first heapify, okay? And then we're basically going to do the pops, pop every element from the heap, except that instead of calling some separate function for pop like we saw earlier, we have access to the internal array for the heap. So we can just do it with the lines 4 and 5 that are shown there on the slide, right? And we're basically swapping the root node with the current last element, if you will, of the heap, and then do fix that, right? So it is conceptually popping every element from the heap in order. Okay, we're just doing code as opposed to calling the pop function earlier, because there's no point. We can just do it right here. So, hope that makes more sense. Wait, I'm confused. What's the difference between Heapify and Heapsort? Okay, yes. Heapify is taking a random array and moving things around such that the array that comes out is an array that behaves the heap order property. Okay, that's very different from sorting. So an array that follows the heap order property is not necessarily sorted. Okay, so that's the difference. Heapify will make sure that the random array turns into a heap, right? But because I'm looking for a sorting, I still need to do something else, and that something else is, well, I'm just going to pop everything out of the heap, right? Which is what we're doing with lines 4 and 5. Okay, and because the array would have had the heap order property, every element that I pop is going to be the most extreme element, and so it comes out in sorted order. And the swap just makes sure that I kind of reuse the same array rather than having to create a separate array. As I pop elements, the swap allows me to reuse the array to place the elements in sorted order. Okay, so I think that answered that. Cool. All right, I have time for one more question if you want to ask it. If not, I encourage you to visit lecture Q&A. It's, you know, I've done a few of those, and they're definitely easier for explaining things without the constraint of time. Is n in the heap size? Is n in the heap size so 9? I believe so. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes, heap size there would be 9. Are heaps used to store data generally? Like, do people do analysis on big data heaps often? So heaps are used often, but they're really useful for specific situations only, right? So the sort of big principle that you want to follow for deciding whether you want a heap is, well, firstly, if you need a priority queue. And you would decide to use a priority queue whenever you need fast access to a most extreme element in a set of elements, right? So in an array, for example. Okay. So that's the specific context in which priority queues shine. So we haven't really shown you an example on when that could be really useful, but when you read Project 2 spec, you will see a very useful scenario in which to use a priority queue. Now, with regards to big data, do people do analysis on big data heaps often? Yeah, the thing. I mean, if you're talking big data, as in potentially having terabytes of data that follow a heap order, I suspect that's really hard to do, and I don't think it would be particularly useful, because if it's big data, everything's really slow, and almost nothing's in memory. So, I mean, if I'm going with the sort of general definition of what big data is. And so there's probably better ways than to try to load everything in memory in a heap. Okay. Are heaps generally only used for priority queues? Yes, I would say yes. I actually wrote a paper in which it used a heap in a somewhat different context. But what remains true is the fact that you use them for when you want, again, fast access to the most extreme element in a set. Right? So any situation which it's going to come up for when we do shortest path, right? So what happens in shortest path is you're in a node in a graph, and you're trying to decide what other node that is adjacent to my current node is the cheapest one to jump to, right? And cheap is defined by the weight of the edge. And so what you would want to do is, hey, if I'm at the current node, I want a priority queue of all the nodes that are adjacent to it so that I can easily figure this out, right? You don't want to have to spend the time moving to a node and then trying to iterate over its adjacent nodes to see which one is the fastest that you can get to, right? Because that would be linear in the number of adjacent nodes that you have. But if you're using a priority queue, that can be done much faster, right? Because all you'd have to do, assuming that you're maintaining your priority queue throughout, is do a quick lookup on top to get the most extreme element. Again, assuming that those elements are your adjacent vertices or nodes. And so that makes it way faster. And we'll get to this in the course for sure. All right, so I will stop it there. Thank you for, I'll leave you with the summary. Thank you for coming. Get ready for project 2. Have a great weekend. I'll see you at office hours Monday. Yep, Monday. All right, catch you all later.